Hey everyone, and welcome to today's Explainer. So today, we're diving into one of the absolute coolest, most visually spectacular experiments you can do in a chemistry lab, the combustion of magnesium ribbon. Now, if you're a Class 10 science student, or honestly, just someone curious about how the physical world works, this is a total rite of passage. But we're not just going to light it up and watch the flashy explosion. We're going to break down the exact mechanics of what happens before, during, and after that spark. Because, in chemistry, the most crucial steps often happen way before the fire is even lit.
So here's a weird question to kick things off. Why on earth would you need to scrub a piece of metal before setting it on fire? It sounds totally counterintuitive, right? I mean, usually, if we want to burn something, like a piece of paper or some wood, we just hold a match to it and boom, fire is fiercely destructive. It just eats right through dirt, grime, whatever's in its way. And yet if you walk into a lab to do this classic experiment, literally the very first instruction is to grab some sandpaper and scrub your fuel. So what exactly is wrong with the metal right out of the jar? Like, what invisible forces are we fighting against here? Well, that's exactly the mystery we're unraveling today.
All right, let's jump right into Section 1, the dull magnesium problem, where we'll be exposing the invisible shield.
When you pull a fresh piece of magnesium ribbon out of its jar, you'd think it'd be this brilliant, shiny piece of metal, right? But it actually looks kind of dull. It has this flat, almost grayish-white matte finish. And here's the thing, that dullness isn't dust, and it's definitely not dirt. As you can see defined here, it's magnesium oxide, or MgO for short. See, the air around us isn't just empty space, it's this crazy soup of reactive gases, especially oxygen. And magnesium, it is incredibly eager to react with that oxygen. So literally just by sitting in a jar exposed to normal air, the outer layer of the magnesium has already reacted. It forms this super thin, really stubborn white coating. It's basically a microscopic, invisible shield wrapped entirely around the ribbon. And that is the core issue here, because this shield is highly unreactive. It just sits there, stubbornly stopping the raw magnesium underneath from catching fire easily when we try to light it. It's kind of like rust forming on a bike, but it happens way faster and acts like a tiny little fireproof blanket.
Which brings us to Section 2, breaking the oxide barrier, or as I like to call it, the sandpaper solution. So picture a student in the lab taking a rough piece of sandpaper and just vigorously rubbing it against that dull strip of metal. Before cleaning, it's coated in that magnesium oxide we were just talking about, and it is just frustratingly unreactive. You could hold the lighter to it all day and it would basically just mock you. But once you apply that mechanical force, you literally scratch that oxide coating right off. You're stripping away the shield, and what's revealed is a beautiful, shiny, pure, and highly reactive strip of fresh magnesium metal. By scrubbing the ribbon, the student is essentially hitting the reset button on the chemical reaction, exposing that vulnerable pure element to the open air once again.
Moving on to Section 3, a dazzling combustion reaction where we are finally lighting the pure metal.
Now visualize this happening in the lab now that our fuel is totally prepped and primed. First off, you secure that newly shiny ribbon with laboratory tongs. And listen, you never ever use bare hands for this, because things are about to get intensely hot. Next, you carefully bring the tip of the ribbon directly over a lit burner. Since we got rid of that pesky shield, the heat interacts directly with the pure magnesium, and suddenly, it catches. You get to observe this absolutely dazzling, blindingly bright white flame. It's truly spectacular. Fun fact, it's actually the exact kind of intense glowing white light that they used in old-fashioned camera flashes. But just as quickly as it starts, it's over. You're left holding tongs that are now gripping nothing but this fragile, crumbly white ash. We collect this ash, which is our final product, white magnesium oxide powder. The actual metal is just completely gone, totally transformed by the fire. And that leads us perfectly into Section 4, chemistry and conclusion. Let's look at the science behind the flame.
Everything we just saw actually builds into a single elegant sentence of chemistry. Check this out. 2Mg plus O2 yields 2MgO. Basically, two atoms of our solid, shiny, freshly sanded magnesium reacting vigorously under the heat of the burner with one molecule of gaseous oxygen from the air, yielding two molecules of solid magnesium oxide. This equation right here is the absolute heart of this whole explainer. Remember that dazzling white light we just talked about? Well, that was the immense energy being released as those magnesium and oxygen atoms literally slammed together to form new chemical bonds. And that white powdery ash we collected at the end? That is the 2MgO. Now here's the crazy part. That is the exact same chemical that made up the dull coating we sanded off at the very beginning. All we did was force the reaction to happen incredibly fast and all at once, which created a massive pile of it instead of just a microscopic little layer. So if you're ever asked to summarize this entire process, like if a teacher or a textbook asks you the golden question on a test, this is the definitive answer you absolutely must remember. Magnesium ribbon is cleaned before burning to remove the magnesium oxide layer so that it burns easily and completely. I really want to emphasize those last two words, easily and completely, because without the sandpaper, the reaction just stutters. It might not catch at all, or it might only burn halfway, basically suffocated by its own protective shield. Cleaning it is what ensures a perfect, complete chemical reaction.
Which actually leaves us with a rather fascinating thought to carry with us today. Look around you right now. The air we breathe is incredibly reactive. I mean, if air can coat a piece of pure magnesium with an invisible, fireproof shield just while it sits safely inside a jar, what other metals in your daily life are hiding beneath invisible chemical shields right now? Is it the aluminum in your soda can, the massive iron beams in a skyscraper? What about the silver jewelry you're wearing? See, chemistry isn't just something that happens with tongs and burners in a lab. It is an ongoing, silent battle happening on the surface of almost everything around us every single second of the day. Definitely keep that in mind the next time you see a piece of metal. Thank you so much for hanging out with me in this explainer, and as always, stay curious.